Here is a curious fact that almost never comes up in ordinary conversation. A single human being, born here on Earth, given the right kind of starship and the right kind of fuel, could in principle travel across the entire observable universe inside one human lifetime. Not as legend, not as metaphor, inside the actual mathematics of the actual world. And yet, by every measurement made from your garden bench, that same person would never move faster than a beam of light. Tonight we are going to walk gently through that contradiction and through the long, strange road that led to it. Before we settle in, leave a quiet note in the comments and tell me what city or small town you are listening from and what the clock reads where you are right now. It quietly fascinates me how these slow stories drift from one dim room into another, across continents, while most of the world is already asleep. Now, take a breath. Let the pace soften. There is no hurry to any of this. The lights in your room can dim a little. The blanket can settle wherever it has fallen. Tonight is one of those nights where you do not need to remember everything. You do not need to understand every word. You only need to follow along, gently, the way you might follow the slow movement of clouds across a pale moon. The question we are circling is enormous, and people have been asking versions of it for centuries. How far can a single person go before death catches up with them? How much of the universe can fit inside one short human life? We will look at that question from many angles. From the angle of old explorers and worn maps. From the angle of rocket engineers in dusty workshops. From the angle of Albert Einstein at a wooden desk in Switzerland. From the angle of astronauts who came home with bones a little thinner than when they left. By the end of the night, you will have a clearer picture of the answer. But you do not have to hold on to it. You can let it drift past you, like a long train of carriages disappearing into the dark countryside. Before we go anywhere abstract, picture something familiar. You are looking up at a clear night sky from a backyard, or maybe from the window of a small flat, or from the wooden steps outside a cabin somewhere quiet. The stars are scattered across the dark, all of them silent. Most of them are so distant that the word distance starts to lose its meaning. There is one bright planet low on the horizon. There is one slow blinking light that you know is a satellite. There is, somewhere up there, the faint dust of the Milky Way, like flowers spilled across a black tablecloth. You feel small under it. Almost everyone does. There is no shame in that feeling. It is one of the oldest feelings our species has ever had. The Babylonians had it. The Egyptians had it. The shepherds on the hills outside Bethlehem had it 2,000 years ago. The Polynesian navigators crossing thousands of miles of dark ocean had it, with nothing but stars to guide them. Each generation looks up at almost the same sky we look at tonight. The question they began asking themselves is the same question we are going to spend tonight on. How far can a person go? How far can a person possibly go? And what is at the end of that going? We will turn that question slowly in our hands, like a stone we found on a beach, and we will look at every facet of it. But here is the thing that takes most people by surprise when they first hear it. The answer to that question depends on who is asking. It depends on whose clock you trust. It depends on whose body you are measuring with. Two people, watching the same starship leave the same launch pad, can disagree about how far it travels and how long it takes, and both of them can be telling the truth. That is not a riddle. That is not a trick. It is the strange, beautiful structure of the universe we happen to live in. The furthest distance a single human could travel within a single lifetime is not one number. It is two. There is the answer measured by the people who stayed on Earth. And there is the answer measured by the traveler, sitting at a window inside her ship, watching the stars stretch into long ribbons of light. Both answers are real. Both answers are part of the same physics. By the end of tonight, you will know exactly why those two answers exist, where they come from, and what the very largest one turns out to be. For now, that is the door we are about to walk through. Slowly, calmly, with the warmth of the room around you. To understand any of this, we have to go back before the word universe was widely used in its modern sense. We have to go back to a world where distance was measured in days of walking, in seasons of sailing, in the swaying steps of a camel across the warm sand of a desert. For most of human history, the very furthest a person could travel in a lifetime was a few thousand miles. There were exceptions, of course, and we will visit some of them. But the average person born in the year 1100 or 1300 or 1500 lived and died within a few days of where they were born. The horizon was the horizon. The sea beyond a certain point was simply where the world stopped. Slowly, and then suddenly, that started to change. Ferdinand Magellan, born in Portugal somewhere around the year 1480, sailed out of Seville in 1519 with 5 ships and around 270 men. His goal was not to circle the globe. His goal was to reach the Spice Islands by sailing west. He never finished the journey himself. He was killed in 1521 in the Philippines, in a shallow fight on a small beach. But one of his ships, the Victoria, under the command of a quiet, careful navigator named Juan Sebastián Elcano, kept going. In September of 1522, 3 years after they had left, the Victoria limped back into Sanlúcar de Barrameda with 18 exhausted men aboard. They had been the first humans to circle the entire planet. The distance they had covered, all told, was about 42,000 miles. For its time, that was almost beyond comprehension. Before Magellan, there had already been other extraordinary travelers, though their journeys were rarely measured. The Polynesian navigators, settling the islands of the Pacific over the course of centuries, crossed thousands of miles of open ocean in long double-hulled canoes called wa'akaulua. Guided by the stars, the swell of the waves, the flight paths of seabirds, and an oral knowledge passed from grandfather to grandchild. They had no compasses. They had no maps in the European sense. And yet they reached, in a slow, deliberate sequence, places as far apart as Hawaii, Easter Island, and New Zealand. From Tahiti to Hawaii alone is more than 2,000 miles of open water, with no land in between. The navigators who first made that crossing, somewhere in the first millennium of the Common Era, did so with skills we still do not fully understand. Their lifetimes, taken as a whole, would have spanned distances comparable to the early European explorers, although in shorter, more rhythmic bursts. There was also Marco Polo, the young Venetian who left home with his father and uncle in the year 1271 and did not return for 24 years. He traveled overland through what we now call Iran and Afghanistan, and the long, dusty roads across Central Asia, reaching the court of Kublai Khan in what is today Beijing. He claimed to have seen sights no European had ever described. The book he dictated after his return, which we now know simply as The Travels of Marco Polo, was read by generations of merchants and explorers in the centuries after. A young Christopher Columbus is said to have kept a personal copy, heavily annotated in the margins. Polo's total distance covered was perhaps 15,000 miles. Modest by modern standards. But it was enough to reshape Europe's understanding of how big the world might be. The Moroccan scholar Ibn Battuta, born in Tangier in 1304, traveled even further. Setting out at the age of 21 to perform the pilgrimage to Mecca, He extended his journey, and then extended it again and then again, until he had visited nearly every part of the known Islamic world and many places beyond it. He saw the Maldives, the coast of East Africa, the rivers of southern Russia, the cities of India, and the seaports of China. He returned home finally, almost 30 years later, having covered an estimated 75,000 miles in total. For 3 centuries, until the great voyages of European discovery, he was probably the most traveled human being on Earth. His memoir, The Rila, gives us a slow, observant, sometimes mischievous picture of a man whose curiosity simply would not let him sit still. 2 centuries after Magellan, the British navigator James Cook would do something similar 3 times across the Pacific Ocean. Born in a small Yorkshire village in 1728, Cook spent most of his adult life on ships. He mapped the eastern coast of Australia. He sailed deep into the Antarctic ice. He died on a beach in Hawaii in 1779. By the time of his death, he had probably traveled further than any human being who had ever lived. His logs estimated he had covered well over 200,000 miles in total. For comparison, that is roughly the distance from the Earth to the Moon. Think about that for a moment. The most traveled human being of the 18th century had, after a lifetime at sea, just barely covered the distance to our closest neighbor in space. The reach of a human life, for almost all of recorded history, was tied to the size of the planet. There was no further to go. The sky was a ceiling, not a destination. And then, in the late 19th and early 20th centuries, something changed. A few quiet thinkers, scattered across Europe and Russia and later America, began to ask whether that ceiling was as solid as everyone assumed. The first of them was a Russian schoolteacher named Konstantin Tsiolkovsky, born in 1857 in a small town called Izhevskoye. He was almost completely deaf from childhood after a bout of scarlet fever, and he taught himself most of what he knew. He worked in a wooden house outside the town of Kaluga, surrounded by notebooks and small experiments. In 1903, the same year the Wright brothers flew their first machine at Kitty Hawk, Tsiolkovsky published a paper that almost no one read at the time. In it, he wrote down what we now call the rocket equation. It is the simple, brutal piece of mathematics that tells you how much fuel a rocket needs to reach a given speed. He also dreamed, in writing, of multi-stage rockets, of orbiting space stations, of colonies far from the Earth. He was, by every measure, decades ahead of his time. He never saw a single rocket fly higher than a small village rooftop. But the equation he wrote down would eventually lift human beings off the planet. Not long after Tsiolkovsky, an American physicist named Robert Goddard began conducting his own experiments. Born in Worcester, Massachusetts in 1882, Goddard was a thin, often sick man with a quiet obsession. As a teenager, he had read H.G. Wells's novel about a Martian invasion, and he reportedly climbed a cherry tree on his family's farm one autumn afternoon and decided, looking up at the sky, that he would devote his life to space travel. He kept that anniversary every year for the rest of his life. He launched the first liquid fuel rocket in 1926 in a field outside the town of Auburn, Massachusetts. It flew for 2.5 seconds. It reached about 41 feet. To everyone watching, it must have looked like a failure. To Goddard, it was a beginning. Around the same time, in Germany, a young engineer named Hermann Oberth was writing books about interplanetary travel and influencing a generation of younger thinkers. Oberth, born in 1894 in what is now Romania, had written his doctoral dissertation on rocket flight to other planets, only to have it rejected as too speculative. He published it anyway, in 1923, under the title By Rocket into Planetary Space. and it became one of the most influential technical books of the 20th century. One of the young men who read Oberth's book and could not put it down was a teenager named Werner von Braun, the son of a German aristocrat, who would, decades later, lead the team that built the Saturn V rocket. As a teenager, von Braun bought a long copper telescope and set it up on the family balcony. He read everything he could find about rockets. By his early 20s, he had joined a group of amateur rocket builders called the Verein für Raumschifffahrt, or the Society for Space Travel, who built small liquid fuel rockets in a deserted ammunition dump outside Berlin. Later, that work was absorbed into the German military, and during the Second World War, von Braun became the technical director of the V2 program at the secret test site of Peenemünde on the Baltic coast. The V2 was the first object built by humans to reach the edge of space. It was also a weapon of war used to bomb London and Antwerp, and built by the forced labor of concentration camp prisoners. That is a heavy stone in the long story of human spaceflight, and it should not be glossed over. After the war, von Braun and many of his colleagues were brought to the United States, where they helped build the rockets that in time would carry American astronauts to the moon. The Saturn V is still the largest, most powerful rocket ever flown by a human-rated mission. It would carry the first humans to the surface of another world. In the Soviet Union, a parallel story was unfolding, often more quietly. A young engineer named Sergei Korolev, born in the Russian Empire in 1907, was building rockets in Moscow in the 1930s. He too was inspired by the writings of Tsiolkovsky. His career was nearly destroyed in 1938, when he was arrested during the Great Purges, accused of sabotage, beaten, and sent to a labor camp in the Russian Far East. He survived the camp, was eventually returned to Moscow, and after the war became the chief designer of the Soviet rocket program. His identity was kept secret from the public for nearly 2 decades. He was never named in official Soviet publications. He was simply called the chief designer. Under his quiet leadership, the Soviet Union launched the first artificial satellite, Sputnik, in 1957. Under his leadership, in 1961, a young pilot named Yuri Gagarin became the first human being to leave the surface of the Earth. Korolev died in 1966, before the moon race was completed, exhausted from years of work and the lingering damage from his time in the camps. He was, in some ways, the man who started the long climb upward. For now, hold the image of all these quiet figures. A deaf Russian schoolteacher writing equations by candlelight. A sickly American climbing a cherry tree to make a private vow. A young German aristocrat with a copper telescope on a balcony. A Soviet engineer in a labor camp in Siberia who would later put the first satellite into orbit. All of them were dreaming, in different languages, about the same thing. A way for a human being to travel further than a human being had ever been allowed to travel before. Now, before we go further into rockets and into Einstein, and into the strange relationship between time and distance, let us slow down and look carefully at the simplest version of the question. If you wanted to know how far a person could travel in their lifetime, the first thing you would reach for is the formula nearly everyone learns in school. Distance equals speed multiplied by time. If you can drive 60 miles per hour for 1 hour, you cover 60 miles. If you can drive 60 miles per hour for 2 hours, you cover 120. Stretch this out. If a person lives for 80 years, and they could somehow move at a constant speed for that entire time, you simply multiply the speed by the duration. That is the answer, in theory. Most of the time, in everyday life, that is also the answer in practice. The trouble starts when the numbers get extreme. Consider what would happen if you tried to scale that idea up to cosmic distances. The fastest object ever built by humans is a small spacecraft called the Parker Solar Probe, launched in 2018. At its peak, while swinging close to the Sun, it moves at around 430,000 miles per hour. That sounds enormous. It is enormous. It is faster than any human-made object in history. But even at that speed, if a single person could somehow ride along inside it for an entire 80-year lifetime, they would only cover about 300 billion miles. That is around 5/100ths of a single light year. 5/100ths, not 5, not 1. Just under 5% of the distance light travels in a single year. And our nearest neighboring star, Proxima Centauri, is more than 4 light years away. So even at the fastest speed any human creation has ever moved, our hypothetical traveler would not even reach the nearest star, let alone the rest of the galaxy. The simple, intuitive picture of distance and time gives us an answer, and that answer is humbling. Without something more interesting going on, the furthest a human could travel in a lifetime is, in cosmic terms, the next room. Not even out the door. Not even off the porch. This is where the story would end, if the universe were as straightforward as our childhood intuitions assume. But it is not. The universe has a built-in feature that almost no one in 1900 could have guessed. That feature is what makes the rest of tonight's story possible. To get there, we need to settle in next to a young man in his mid-20s, working as a clerk in a patent office in Bern, Switzerland. The year is 1905. The man's name is Albert Einstein. He is 26 years old, married to a young Serbian woman named Mileva, and the father of an infant son named Hans Albert. He is not a famous scientist. He is, in fact, almost completely outside the academic establishment. He has tried for years to find a teaching post at a university and failed. So he sits 6 days a week at a wooden desk on the second floor of the Federal Office for Intellectual Property, reading the patent applications of inventors. Many of the applications are for devices that synchronize clocks at a distance. Railway companies, in particular, need to know that 2 clocks in 2 different cities are showing the same time, so that trains can run on schedule. Einstein reads these patents carefully. He also thinks, in his off hours, about a question that has been bothering him for years. What would happen if a person tried to chase a beam of light? What would the light look like? Would it appear frozen? Would it stop? Would it behave as if it were standing still in midair? In the spring of that year, in a series of papers that he later jokingly called his miracle, Einstein gave the world the answer. The answer was that no matter how fast you tried to chase the light would still appear to move at the same speed past you, always, in every direction, from every observer's point of view. That speed, which we now write as a constant called c, is roughly 670 million miles per hour. Nothing material can move quite that fast. Light always does, and there is no way to catch it. This sounds, the first time you hear it, like a strange technicality. But the consequences are enormous, and they reach right down into the question we are circling tonight. If everyone has to agree that light always moves at the same speed, then other things have to give. In particular, 2 things have to give. Time has to give, and space has to give. Both of them, it turns out, are stretchable. Both of them, it turns out, are not what we thought they were. Einstein was not alone in this work. Several other physicists, in the years leading up to 1905, had been circling the same questions. Hendrik Lorentz, a quiet Dutchman in Leiden, had already written down most of the mathematical equations describing how space and time would have to change in order to keep the speed of light constant. He published his version in 1904. The transformations are now named after him. Henri Poincaré, the French mathematician and polymath, had also been writing in elegant and careful French about a new principle of relativity and about the symmetries that would have to govern such a theory. Some historians of science argue that Lorentz and Poincaré, taken together, had laid out almost all the pieces of the picture by 1905. What Einstein did in his quiet patent office was to take the leap of treating those pieces not as mathematical tricks for explaining a strange experiment, but as the literal structure of reality. Time really does slow down. Space really does compress, not as an artifact of measurement, as the truth of what is. A few years later, in 1908, a German mathematician named Hermann Minkowski, who had once been one of Einstein's professors at the Swiss Polytechnic and had reportedly called the young Einstein a lazy dog, took the theory and reshaped it again. Minkowski showed that space and time in Einstein's relativity were not two separate things at all. They were aspects of a single, unified, four-dimensional structure he called space-time. Events did not happen at a place and a time. They happened at a point in space-time. Distance and duration were not absolute. They were shadows cast by something deeper. Einstein, who had at first been skeptical of Minkowski's reformulation, came to embrace it, and it became the foundation for his work on general relativity a decade later. Minkowski himself did not live to see how far the theory would go. He died in 1909, at the age of 44, of a sudden infection. The pace at which physics was changing in those years was extraordinary. So was the pace at which the people who were changing it were losing each other. Here is the simplest way to begin to picture this, before we get into any of the harder details. Imagine you are standing on a quiet train platform on a still evening, and a long train is rushing through the station without stopping. Inside one of the cars, a passenger is sitting and looking down at her wristwatch. From her point of view, time on her watch is ticking along the way it always does. The second hand sweeps around steadily. She's unhurried. She glances out the window at the lights of the station blurring past. From your point of view on the platform, however, something subtle is happening. If you could somehow see her watch in detail, you would find that her watch is ticking just slightly more slowly than yours. Not because anything is wrong with the watch. The watch is fine. It is the time that has changed. The faster she moves relative to you, the slower her clock ticks compared to yours. At ordinary train speeds, the effect is so tiny that no one would ever notice it. The difference is less than a single second across many lifetimes. But the effect is real. We have measured it. We measure it routinely with atomic clocks flown on airplanes around the world. It is not a story. It is not a metaphor. It is the actual behavior of the universe at its most basic level. Now, take that idea and scale it up. Suppose, instead of a train, we are talking about a starship moving at half the speed of light. The effect would be much more obvious. Clocks on board the ship would tick noticeably more slowly than clocks left behind on Earth. Push the speed higher, to 90% of the speed of light, and the difference becomes dramatic. A year of ship time would correspond to more than 2 years of Earth time. Push the speed to 99%, and the gap widens further. A year of ship time would correspond to roughly 7 years of Earth time. The closer the ship gets to the speed of light, the more pronounced the effect becomes, the same way a curve grows steeper and steeper as you approach a wall. The mathematical expression for this is called the Lorentz factor, after the Dutch physicist Hendrik Lorentz we mentioned a moment ago. The Lorentz factor is just a number. At ordinary speeds, it is almost exactly 1, which is why we never notice it. At very high speeds, it can grow into the dozens, the hundreds, the thousands. It can grow, in principle, as large as you like. If you are wondering whether all of this is just clever mathematics rather than something that really happens, here is the small, beautiful piece of experimental evidence that quietly settles the question. There is a kind of particle called a muon. Muons are produced high in the Earth's upper atmosphere when cosmic rays from outer space slam into atoms of nitrogen and oxygen. Muons are unstable. In a laboratory at rest, a muon survives, on average, for about 2/millionths of a second before it falls apart into smaller particles. 2/millionths of a second is not much time. At nearly the speed of light, a muon could only travel about half a kilometer in that time before it was gone. By that measure, the muons created at the top of the atmosphere should not survive long enough to reach the ground. They should, by every classical estimate, decay long before we could detect them. And yet, every second of every day, muons from the upper atmosphere are passing right through your body at sea level. Hundreds of them, every second, through every square meter. We can measure them with simple particle detectors. The reason they make it down is precisely the time dilation we have been talking about. From our point of view, on the ground, the muons are moving so fast that their internal clocks have slowed dramatically. They live much longer in our reference frame than they would if they were sitting still. From their own point of view, they live the same brief life they always live. But the distance from the top of the atmosphere to the ground has compressed, so they can cross it before their clock runs out. Both perspectives agree. The muons arrive. Einstein was right, and that proof has been sitting quietly above your head, falling through your hair, for as long as you have been alive. Now, here's the thing that surprises almost everyone. The slower the traveler's clock ticks compared to people back home, the further she can travel during her own personal lifetime. From her point of view, she is not aging more slowly. She is just aging normally, the way anyone ages. Her hair grays, her hands wrinkle, her bones lengthen and then settle, the way human bones do. But the universe outside her ship is, from her perspective, getting more compact. Distances that, to a person on Earth, look like dozens of light years, to her look smaller. The galaxy is being squeezed in the direction of her motion. Not for everyone, not in any objective way. Only for her, only along the line she is moving in. And so, if she can keep accelerating, the destination keeps drawing closer. By her clock, the trip takes less and less time. By the clocks left behind, the trip takes more and more. Both clocks are right. The universe simply does not have a single, agreed-upon stopwatch. This is the moment where, in almost every conversation about relativity, somebody asks the obvious follow-up. If both clocks are right and motion is relative, then could not the traveler equally say that she is sitting still, and the Earth is the one moving away from her at nearly the speed of light? If so, would not the Earth's clock be the one ticking slowly, from her point of view? And if that is true, then which clock is really slower? This is what is usually called the twin paradox. Imagine identical twins, one of whom stays at home on Earth, while the other climbs into a starship and travels at very high speed to a distant star and then comes back. When they meet again, who has aged more? Both of them have been moving relative to the other. So why is it always the traveler and not the stay-at-home twin who comes back young? The answer, when you settle into it, is one of the most lovely details in the whole theory. The two situations are not actually symmetric, even though they look like it at first. The twin who stays on Earth experiences one steady frame of reference for the entire trip. The twin who travels does not. She accelerates away from Earth. She turns around at the distant star. She accelerates back. Each of those changes of motion shifts her perspective in a measurable way. The acceleration is what breaks the symmetry. The traveler is the one who has to lean against the back of her chair when the engines fire. The traveler is the one whose tea spills if she does not hold it carefully during the turnaround. The traveler is, in the deepest sense, the one whose path through space-time bends. And because of the way space-time is shaped under Einstein's rules, the bent path is always the shorter path in time. So she comes home young, and her sibling, who has been sitting in a kitchen all those years drinking tea and watching the snow fall outside, has grown old. This has been confirmed experimentally many times, using atomic clocks flown around the world on commercial jets. Flying clocks come back showing a slightly different time than clocks left on the ground. Not by enough to matter to anyone's daily life, but by enough to settle the question, finally, in the records of every atomic clock laboratory on the planet. If that idea feels strange the first time you hear it, that is normal. It felt strange to physicists in 1905. It felt strange to Einstein himself in his quieter moments. The universe does not owe us intuitive sense. It only owes us consistency. And consistency in this case requires that clocks on different paths through space-time show different times when they meet up again. There is no paradox. There is only the geometry of space-time doing what space-time does. This is the strange, lovely, dizzying truth that quietly underpins the entire rest of tonight's story. So before we keep going, take one more breath, let it out slowly, and let your shoulders settle back into the pillow. There is no test. There is no quiz. There is only the slow walking through of a beautiful idea. To make the idea more concrete, here is an analogy you can play with quietly in your mind. Picture a long, narrow corridor stretched out in front of you, lined with floor lamps on each side. The lamps are spaced about 10 paces apart. You start to walk. With each step, you can count the lamps as you pass them. 1 lamp, 2 lamps, 10 lamps, 20 lamps. The corridor is long, but the lamps go on forever. Now imagine that as you walk faster, the corridor itself begins to shorten in your direction. The far end starts to inch toward you. Not visibly bend, just slightly compress, like a paper accordion being squeezed from both ends. If you walk slowly, you barely notice anything. If you walk much faster, the compression becomes obvious. By the time you are running flat out, the corridor looks short. You arrive at the far end in only a handful of steps. Meanwhile, someone standing outside the corridor, watching you through a window, sees something different. From their view, the corridor is the same length it always was. You, the runner, are the one who has become compressed, flattened in the direction of motion, and your steps are taking longer than you think they are. From their view, your trip across the corridor took ages. From yours, it was quick. Both views are correct. They cannot be reconciled by saying that one of you is wrong, because neither of you is wrong. They are reconciled by accepting that distance and time are different for the two of you. The corridor, of course, is not really a corridor. It is space. The lamps are not lamps. They are stars and planets and dust clouds and the occasional drifting body of ice. The runner is the traveler in the starship. The watcher is anyone left back on Earth. The compression of the corridor is what physicists call length contraction. It is the second half of the same effect that made the watch tick more slowly. Time stretches, distance shrinks. The two effects are tied together by the same simple rule. The faster you move, the more your clock slows and the more your road compresses. And if you can keep pushing closer to the speed of light, the compression and the slowing keep deepening without any hard ceiling. There is no maximum to how strong the effect can get, as long as you keep adding more energy and more fuel. Now, somewhere around this point in the story, most people quietly ask the same question. If all of this is real, why don't we notice it? Why don't our daily lives feel strange? Why is the morning kettle and the closing of the front door and the slow shuffle to bed all so reassuringly steady? The answer is that the speeds of ordinary life are tiny compared to the speed of light. A car at 60 miles per hour is moving at roughly 1/10 millionth of the speed of light. A passenger jet at 600 miles per hour is just a few times faster than that. Even the fastest fighter jets only crack a small fraction of 1% of the speed of light. At these speeds, the time dilation effect amounts to billionths of a second over an entire human life. It is real, but it is invisible to anything we ordinarily measure. The universe lets us live in a comfortable approximation, where time and distance behave the way our ancestors thought they did. It only reveals its strange face when we push close to the edge. And here is the thing that is easy to miss. For most of human history, no one even came close to that edge. Even the fastest mounted couriers, the fastest carrier pigeons, the fastest trains, were all so far below the speed of light that the universe's hidden behavior was utterly invisible. It took the experiments of the late 19th century, especially the work of two Americans named Albert Michelson and Edward Morley, to start to see the cracks. In 1887, in a laboratory in Ohio, Michelson and Morley tried to measure the speed of the Earth's motion through what they thought was a kind of invisible cosmic medium. They expected to find that light moved differently depending on the direction. They found, instead, that light moved at exactly the same speed in every direction. That puzzling, almost embarrassing result sat in physics for nearly 2 decades before Einstein, in his little office in Bern, looked at it and said, calmly, "Perhaps the universe is simply built that way." He was, of course, correct. Now, having all of this in place, we can start to imagine what would actually happen to a person who tried to travel as far as possible inside a single lifetime. Suppose, for the sake of imagination, that we had a starship powerful enough to accelerate at one Earth gravity continuously for years. The acceleration would feel exactly like ordinary weight on the floor of the ship. You could pour a cup of tea. You could walk across a hallway. You could lie down on a bed and sleep without floating off into the air. There would be nothing visibly extreme about life on board, except for what was happening outside the windows. The ship would steadily build speed, and the universe outside would begin to behave in the strange way we just described. Within about a year of ship time, the ship would be moving at close to the speed of light. From that point on, the time dilation effect would deepen rapidly. After a few more years, distances that look enormous from Earth would start, from inside the ship, to compress into something more manageable. Here is what the math of this actually predicts, and it is one of the most beautiful results of 20th century physics. With a constant 1g of acceleration, with no real concern for fuel for the moment, a traveler could reach our nearest star system, Alpha Centauri, in just under 4 years of her own time. She could reach the center of our galaxy in around 20 years of her own time. She could cross to the great spiral galaxy of Andromeda, 2.5 million light-years away, in about 28 years of her own time. And if she kept going, she could in principle reach the very edge of the observable universe in roughly 45 years of her own time. That is the answer the equations give. 45 years, less than a single human lifetime, less than the working career of a doctor or a teacher or a carpenter. In her own experience, she would not have aged unusually. She would have grown older the way anyone grows older, just inside a ship rather than inside a house. That is the largest answer to our question. That is the furthest a human could, in principle, travel, measured by the traveler's own life. The entire visible universe. Every galaxy you can see in any photograph from the Hubble Space Telescope or the James Webb. Every distant smudge in the deep field images, where the universe looks more like a quiet bowl of glowing dust than anything resembling a starry sky. All of it. Crossable in principle by one person in the span of one lifetime. You can take a moment with that. Let it sit in the dim air of the room. There is no rush. Of course, the answer measured by people back on Earth is very different. From the Earth's point of view, the trip across the entire visible universe would take billions of years. Billions. Most of the stars that surrounded our traveler at the start of the trip would by then be dead. The sun itself would have swelled and shed its outer layers. The Earth would, in some form, be unrecognizable. From the outside, the trip would be unimaginably long. From the inside, it would be the work of a single human life. Both pictures are true. Both clocks are correct. The universe simply does not contain a single shared time. And so, when people ask, how far could a human travel in a single lifetime? The honest answer is, it depends on whose lifetime you mean. But before you let that result settle into a final shape, we have to slow down and look at all of the reasons this is not quite as simple as the math suggests. Because the moment you try to build the ship, the equation begins to sweat. The moment you try to fuel the ship, the equation begins to wince. And the moment you put a real human inside the ship, with real bones and real blood and a real beating heart, the equation begins to look you in the eye and say, you have not yet thought of everything. We have a long, slow road ahead of us, made up of three big problems: the fuel problem, the body problem, and the radiation problem. We will take each of them in turn, gently, the way you might walk through 3 quiet rooms in an old house. Let your eyes rest. There is nothing here you have to memorize. There is nothing here that requires effort. We are only walking through. The fuel problem is the most famous of the 3, and it is the one that physicists and engineers have circled most often. To accelerate a starship at 1G for years on end, you need an enormous amount of energy. Even if your engine were perfectly efficient and could convert mass directly into useful thrust with no waste, the amount of fuel you would have to carry quickly becomes absurd. To accelerate a small starship to a useful fraction of the speed of light, you might need a quantity of fuel many times the mass of the ship itself. To accelerate continuously for decades, the fuel mass becomes truly enormous. And here is the catch that makes the problem worse than it looks. The more fuel you carry, the heavier the ship becomes, and the more fuel you need to push that fuel along with you. The rocket equation, the one Tsiolkovsky wrote down in 1903 in his quiet wooden house, is unforgiving about this. It is the tyranny that every space mission designer learns to respect. You cannot simply pile on more fuel without paying a steep, exponential price. There have been some elegant proposals for ways around this. One of them, suggested by an American physicist named Robert Bussard in 1960, imagined a starship with an enormous magnetic scoop on the front. The scoop would gather thin clouds of hydrogen from interstellar space, feed them into a fusion engine, and use them as fuel as the ship moved. The idea was beautiful. It looked on paper like a way to travel almost indefinitely without carrying all the fuel along from the start. Later work, however, suggested that the magnetic scoop would create more drag than thrust, slowing the ship down rather than speeding it up. So this idea, like many lovely ideas in physics, sat back down on the bench and watched the others play. Another proposal involved the use of antimatter. Antimatter, when it meets ordinary matter, releases energy with almost perfect efficiency. A single gram of antimatter, fully reacted with a single gram of ordinary matter, would release the energy equivalent of dozens of kilotons of high explosive. The trouble is that antimatter is extremely difficult to make. As of today, the entire amount produced by all the world's laboratories combined would not fill a thimble. And storing it is even harder than producing it, because antimatter explodes the moment it touches any ordinary surface. So antimatter, too, remains a beautiful idea that does not yet fit into the world we live in. The body problem is older and more stubborn. Even setting fuel aside, the human body is not built to live for years at a stretch in deep space. We have learned this slowly, through experience, on the Mir space station and the International Space Station and the Salyut stations before them. The longest single space mission ever flown by a human was carried out by a Russian doctor and cosmonaut named Valery Polyakov, who lived on Mir for 437 days between 1994 and 1995. He came home, walked unsteadily on his own 2 feet, and is widely considered one of the toughest space travelers in history. But his body had changed. His bones had lost density. His heart had grown slightly smaller. The muscles around his back and legs had thinned despite hours of daily exercise. He recovered in time. But the lesson was clear. The longer the body floats in zero gravity, the more the systems we evolved to use under 1G start to fade. Another cosmonaut, Sergei Krikalev, eventually accumulated more than 800 days in space across multiple missions. He is sometimes called the most time-traveled human in history because the time dilation effects of his fast orbital motion, although extremely small, have nonetheless aged him by a few tens of milliseconds less than he would have aged on the ground. That is, in a small and very real sense, time travel. A man who lived through events on Earth a few tens of milliseconds after most of the rest of us did. It is not science fiction. It is not a thought experiment. It is recorded in the orbital logs and atomic clocks of multiple national space programs. The effect is small, but it is the first faint thread of the same effect that, on a much grander scale, would let our hypothetical traveler cross the universe in a single lifetime. Krikalev's story has another, quieter twist that fits the night. He was on board the Mir space station in 1991, orbiting peacefully overhead, when the Soviet Union dissolved beneath him. The country that had launched him no longer existed by the time he came home. The city where he had trained, then called Leningrad, had been renamed St. Petersburg. The currency had changed. The political system had changed. He spent 10 months in space on a mission that was originally meant to last 5, because the ground crew had to keep figuring out who, exactly, was paying for it, and who, exactly, was going to bring him back. He landed in March of 1992 in the cold steppes of Kazakhstan, in a country that did not yet know what it was. The press at the time called him the last citizen of the Soviet Union. He had simply gone to work, in orbit, and the world around his work had shifted while he was looking the other way. There is something quietly powerful in that image. A small, ordinary man, in a small, ordinary capsule, becoming a witness, almost by accident, to a kind of historical time dilation of his own. Before Krikalev, before Polyakov, before any of the long-duration cosmonauts, there was the small American space station called Skylab. Skylab was launched in 1973 on the last available Saturn V, the very same rocket family that had carried the Apollo astronauts to the moon. It was the United States' first attempt at having astronauts live in space for weeks at a time. 3 crews flew up to it across 1973 and 1974. The third crew, made up of Gerald Carr, Edward Gibson, and William Pogue, spent 84 days in orbit, which at the time was a world record. They had grown small private gardens in plastic boxes. They had floated through the open volume of the station, learning how their muscles worked in zero gravity. They had also, partway through the mission, staged what we might now call the first labor action in space. They felt overworked. They had not been given enough rest. So one quiet afternoon, they simply stopped talking to Mission Control for several hours and looked out the window at the Earth turning slowly below. When they finally came home, the lessons from their experience shaped almost every long-duration mission that has followed since. The body, the mind, and the schedule all needed to be respected. In the years that followed, the Soviet Union ran a long, careful sequence of stations called Salyut. The first, Salyut 1, was launched in 1971. The crew sent to visit it, Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev, were the first humans to live aboard a space station. On their way home, a faulty valve opened too early on their Soyuz capsule, exposing them to the vacuum of space. All 3 died, silently, in their seats, in less than a minute. They are still the only humans ever to have died outside the Earth's atmosphere. Salyut 1 was later allowed to burn up in the atmosphere, but the program continued through Salyut 6, Salyut 7, and finally Mir, which was launched in 1986 and which stayed in orbit until 2001. The International Space Station, jointly operated by Russia, the United States, Europe, Japan, and Canada, has been continuously inhabited since November of the year 2000. There has not been a single moment in more than 2 decades when there were no humans living above the Earth. There are also other quieter problems with the body in deep space, problems that did not even appear in the books and films of the 1960s and 1970s, because we did not yet know about them. One of these is called spaceflight-associated neuroocular syndrome, when astronauts spend many months in weightlessness. The fluid inside their bodies drifts upward toward the head instead of being pulled down by gravity. The pressure inside their skulls rises slightly. The shape of the back of their eyeballs changes. Their optic nerves swell. Many astronauts return from long missions with eyesight that is slightly worse than when they left. Some of the damage is permanent. The eyes are sensitive instruments, and they were tuned over millions of years of evolution for the inside of a gravity well. They do not always like the experience of leaving one. Another problem is the way the heart adapts. In zero gravity, the heart does not need to pump as hard to move blood up to the brain. Over months, the heart muscles weaken slightly. The shape of the heart itself, which on Earth is roughly elongated like a small pear, gradually becomes more spherical, more like a small grapefruit. This is not on its own immediately dangerous, but it shows how quickly the body remodels itself in response to a different environment. The bone story is similar. Astronauts can lose around 1 to 2% of their bone mineral density per month in zero gravity, mostly in the bones that bear weight on Earth, like the hips and the lower spine. This is a rate of loss similar to what people on Earth experience over a year of severe osteoporosis. The countermeasures, like long sessions on resistance machines bolted to the floor, only partly offset it. After a year in space, an astronaut's bones look on a scan like the bones of someone 2 or 3 decades older. There are smaller, stranger problems too. The immune system, lulled by the absence of the constant low-grade challenges it faces on Earth, often slacks off in space. Dormant viruses can reactivate. Latent infections can rear back up. The microbes living on the skin and in the gut shift in their balance. sometimes in ways that are not yet fully understood. The bacteria themselves, free of gravity, sometimes behave more aggressively, growing thicker biofilms on surfaces, becoming, in some studies, more resistant to antibiotics. Even on a relatively safe space station only a few hundred miles above the Earth, the human body never quite forgets that it is somewhere it does not belong. On a starship crossing interstellar distances, those small daily wear marks would accumulate into something far more serious. Now, the radiation problem is in some ways the quietest and the most threatening. In the absence of Earth's atmosphere and its magnetic field, space is full of high-energy particles. Some come from the sun. Some come from distant, ancient explosions. Some come from the cores of dying stars on the other side of the galaxy. They are called cosmic rays, although they are not really rays. They are tiny, fast-moving protons and atomic nuclei, traveling at close to the speed of light, smashing into anything they meet. On Earth, the atmosphere absorbs most of them before they can reach us. In a starship, with only walls of metal and water around the crew, the radiation steadily accumulates inside the bodies of the travelers, year after year. It damages tissue. It increases the risk of cancer. It can interfere with the workings of the central nervous system. The further from the sun a ship gets, the better protected it is from solar radiation. But the more exposed it becomes to the background hum of high-energy particles from elsewhere in the galaxy. Engineers have proposed shields of water, of liquid hydrogen, of magnetic fields generated by superconducting coils. Each idea has its own weight and complexity. Each one would add mass to the ship, and so eat away at the fuel budget. None of them, with today's technology, completely solves the problem. There is another way around the whole question of speed, by the way, which we should at least mention before we move on. Instead of building a fast ship, you could build a slow ship that lasts a very long time. The traveler would not finish the journey themselves. Their descendants would. This is what science fiction writers call a generation ship. A small, self-contained community would live and work and raise children inside the vessel, generation after generation, for centuries or even millennia, while the ship slowly crossed the gap between stars. There would be no time dilation to speak of, because the ship would never get very close to the speed of light. The original travelers would die. Their children would be born under the strange flickering lights of the corridors. Their children's children would grow up knowing only the ship as home. Eventually, after 20 or 30 generations, a distant descendant of the original crew would arrive at the destination, having never seen the Earth, having never breathed open air, having never walked under a real sky. The total distance covered by that ship would not be a single human lifetime's reach. It would be a kind of relay, passed from hand to hand to hand. Whether such a journey would still count as a single human life. Crossing the gap is a question we do not really have a clean answer to. It is, perhaps, a different kind of furthest distance. Not the furthest reach of one body, but the furthest reach of one continuing lineage. Both kinds of reaching are part of what we are as a species. So when we say, in cool, abstract terms, that a human could travel across the visible universe in a single lifetime, what we really mean is that the mathematics of physics allows it. The mathematics says nothing about whether we can build the ship, fuel the ship, or keep the people inside it alive. Those are separate problems. They are engineering and biology problems. And they are very, very hard. As of tonight, in your house, on your couch, in your warm bed, no spacecraft we have ever built has come even remotely close to the speed required. The fastest one, the Parker Solar Probe, is moving at less than 1/10,000th of the speed of light. The Voyager 1 probe, launched in 1977, has spent more than 4 decades drifting outward and is now over 15 billion miles from home. It is still inside our own local neighborhood. To reach our nearest neighbor star, even continuing at its current speed, would take Voyager 1 around 73,000 years. 40 centuries times 18. That is a long time. That is roughly the entire span of recorded human history, repeated dozens of times over. And Voyager 1 will not reach Proxima Centauri. It is not aimed there. It is, instead, drifting slowly toward a faint star called Gliese 445, which it will pass at a distance of about 1.5 light years, in about 40,000 years. By then, the small plutonium battery powering its electronics will have been silent for tens of thousands of years. The probe will continue to drift, frozen, quiet, a tiny golden record from a long-vanished world tucked inside it. If you find a moment of stillness here, let yourself stay in it. There is something tender about that image. A small machine the size of a refrigerator, traveling for tens of thousands of years through emptiness, carrying inside it the sounds of children laughing in many languages, the chime of a bicycle bell, a brief recording of Chuck Berry's guitar, and a greeting from a long-dead United Nations Secretary General. Voyager is, in a real sense, the furthest a piece of human craftsmanship has ever traveled. And by far, the furthest it ever will, for any spacecraft we are likely to launch in the next century. The question of whether any human will ever ride along with it in some future version is still wide open. The golden record itself is worth lingering on for a moment because it was assembled by a small group of people who knew it was almost certainly never going to be found. And they assembled it lovingly anyway. The project was led by the American astronomer Carl Sagan, who was at the time a professor at Cornell University, along with his wife and collaborator Linda Salzman Sagan, the writer Anne Druyan, the science writer Timothy Ferris, and the artist John Lomberg. They spent months gathering material. They included greetings in 55 languages, from ancient Akkadian to modern Mandarin. They included natural sounds, like surf on a beach, thunder over a forest, a kiss between two people, the call of a humpback whale. They included 115 images encoded onto the record, showing everything from a fertilized egg dividing to a Saturn V on the launch pad, to a woman shopping for groceries in a supermarket. They included nearly 90 minutes of music, with selections from Bach and Beethoven and Mozart, along with Australian Aboriginal songs, a Navajo night chant, a Senegalese percussion piece, a Peruvian wedding song, Indian raga, Azerbaijani folk music, and Chuck Berry's Johnny B. Good. There is also, recorded onto the metal of the disc itself, the brainwaves of Anne Druyan, taken during an hour-long meditation in which she thought about everything she could remember about her life, including the fact that she had just, days before, become engaged to Carl Sagan. She has said, in interviews since, that for that hour her brain was full of him. Whoever, in some unimaginable future, ever decodes that record will be receiving, among everything else, the inside of a single human heart, in love, for an afternoon. So far, we have followed 2 parallel paths. One is the path of mathematics, which says that if we could accelerate continuously at 1g, we could cross the universe in a single lifetime. The other is the path of engineering, which says that we cannot yet build the ship to do that, and possibly never will. There is a third path, which is the path of what we have actually achieved. And it is, by comparison, very modest. Let us walk through that path slowly, because it has its own quiet beauty. The furthest human beings have ever traveled, in terms of their distance from the Earth, are the crew of Apollo 13. Their mission launched in April of 1970, was supposed to land on the moon. 2 days into the flight, a faulty oxygen tank ruptured deep inside the service module. The crew spent the next 4 days nursing their crippled ship around the backside of the moon and back home to Earth. Because of the loop they were forced to take, the 3 astronauts, James Lovell, Jack Swigert, and Fred Hayes, passed at a greater distance from Earth than any humans before or since. At their furthest point, on April 15, 1970, they were about 248,000 miles from home, on the far side of the moon, in radio shadow. Looking down at the dim, cratered surface of a place no one had yet successfully landed. That distance, 248,000 miles, is the official record. It has stood for more than 5 decades. It is worth pausing on the people involved here, because the records were not set by professional explorers or trained adventurers in the romantic sense. They were set by working pilots, mostly former military test pilots, who had been chosen by a careful, almost dry selection process and had spent years preparing for missions that were, in many cases, quite different from the ones they actually flew. Jim Lovell, the commander of Apollo 13, had grown up in Cleveland, Ohio, the only son of a single mother who worked as a switchboard operator. He had wanted to be an astronaut before there was such a job. He had flown on Apollo 8 in 1968, becoming one of the first 3 humans to leave Earth orbit and travel to the moon. He was, by the time of Apollo 13, the most experienced spacecraft pilot in the world. Jack Swigert was a bachelor from Denver, Colorado, a quiet engineer who had been added to the crew at the last minute, replacing another astronaut who had been exposed to measles. Fred Hayes was a Mississippi-born former Marine, a man with a slow Southern voice and a careful hand on the controls. None of them ever returned to the moon. Apollo 13 was, in a small mercy, the only Apollo mission that did not result in any deaths, despite coming closer than any other to disaster. The Apollo program itself, taken as a whole, was perhaps the most concentrated push of human travel in the history of our species. In a little under 4 years, between July of 1969 and December of 1972, 24 men flew to the moon. 12 of them walked on its surface. None of them were over the age of 47. The youngest, Charlie Duke, was 36 when he walked on the moon during Apollo 16. By the end of the program, the last astronauts to leave the lunar surface, Eugene Cernan and Harrison Schmitt of Apollo 17, drove around in a small electric rover, gathered hundreds of pounds of rocks, and stayed for 3 full days. Then they climbed back into their tiny landing craft, lifted off in a small puff of dust, and returned home. No human has been back to the moon since. The footprints they left behind, because there is no wind and no rain on the moon, are still there, exactly where they were pressed into the gray dust in December of 1972. They will still be there, more or less unchanged, when our own great-grandchildren are old. The fastest a human being has ever moved, relative to the Earth, was during the return of Apollo 10 in May of 1969. The crew of that mission, Thomas Stafford, John Young, and Eugene Cernan, were on a kind of dress rehearsal for the moon landing 2 months later. On the way back, their command module reached a peak speed of about 24,790 miles per hour. That is roughly 30 times the speed of a rifle bullet. It is also about 0.037% of the speed of light. As you can see, even our fastest crewed mission is hopelessly slow compared to the speeds at which time dilation begins to matter. The records, while impressive, are still firmly inside the realm of horse-drawn time. We have, for now, only really left the porch. The longest cumulative time a single person has spent in space was set by Oleg Kononenko, who, by 2024, had spent more than 1,100 days in orbit across multiple missions. The total distance he has traveled along his orbital paths, taken together, is something approaching 500 million miles. That number sounds enormous. But almost all of it was, of course, simply running around and around the Earth, like a runner doing laps on a track. It is not the same as crossing space outward. He covered the equivalent of many round trips to the Sun. But, as in the analogy of Captain Cook crossing back and forth across the Pacific, the distance covered is not the same as the distance outward from home. If you put it all together, here is the rough picture of the furthest human travel as of this evening. The furthest from Earth a human has reached is about 250,000 miles. The fastest a human has moved is about 25,000 miles per hour. The longest continuous time a human has spent in space is about 1.5 years. The total cumulative time a human has spent in space is about 3 years. The total distance a person has traveled in space over a career is a few 100 million miles, mostly in circles. Compared to the distances and speeds we have been discussing, all of these numbers are tiny. We are still, by every measure, very young in the matter of leaving home. Now, sit with that for a moment. Notice how strange it is. The mathematics of the universe permits us, in principle, to cross the entire visible cosmos within a lifetime. And the reality of our current toolkit does not yet permit us to even leave the corner of our own solar system. Both of those statements are true at the same time. They are not in conflict. They simply describe different layers of the question. The first is about what the universe allows. The second is about what we have figured out how to do. Let us go back, for a few minutes, to the mathematics, and look more carefully at the answer it gives. Because the picture is even stranger and lovelier than we have so far described. Suppose our hypothetical traveler steps into her ship, closes the door, and begins to accelerate at 1 g away from the Earth. She has, let us say, an infinite supply of fuel, and an engine that converts that fuel into thrust with perfect efficiency. We will not worry for now about how she got that supply. We will just imagine that, somehow, she has it. After 1 year of her own time on board, she will already be moving at about 3/4 of the speed of light. After 2 years of her own time, she will be at around 97%. After 3 years, she will be deep into the realm where the Lorentz factor begins to climb steeply. By the time 5 years have passed for her, the ship will be moving at speeds where every passing decade of her life corresponds to centuries on Earth. After 10 years, that ratio grows to thousands. After 20 years, to millions. By the time she is aged 30 or 40 years inside the ship, the universe outside is aged by tens of billions of years. This is not a paradox. This is, again, simply how the world is built. The two clocks disagree. The traveler is not freezing time. She is not pausing the universe. The universe is doing its usual thing. It is the Earth's clocks that are doing the usual thing too. What is different is the comparison between them. If she were to look back at the Earth through a powerful telescope, she would see history unspooling backwards as the light from the Earth reaches her over longer and longer paths. She would see cities rise and fall. She would see continents shift. She would see, perhaps, the slow swelling of the sun as it begins, billions of years from now, to enter its red giant phase. She would see all of this not as a movie playing at normal speed, but as a long, complex, distorted sequence of images stretched out by her own motion. If she ever turned around and tried to come back, she would arrive at an Earth that no longer exists in any recognizable form. she would not be able to go home. There would be no home left to go to. That is part of the price of going so far so fast. The destination she could reach, in principle, would depend on how long she was willing to spend traveling. If she wanted to reach the next nearest star, only a few years of her time would be required. If she wanted to reach the center of the galaxy, around 20 years. If she wanted to reach the Andromeda galaxy, around 28 years. If she wanted to reach a galaxy 10 billion light-years away, around 40 years. If she wanted to reach the very edge of the observable universe, around 45 years. Each of those numbers comes out of the equations of relativistic motion under constant acceleration. They are simple, if a bit tedious, to derive. They are also exact. Within the rules of physics, as we currently understand them, those numbers are the answer. And here is the thing that I find quietly moving every time I sit with it. The whole observable universe is, in this sense, within reach of one human life. Not within the reach of human bodies as they exist today. Not within the reach of engineering as it exists today. But within the reach of one lifetime, mathematically speaking. The universe has, baked into its own rules, the possibility of being crossed by a single person. It is not a hostile, infinite expanse forever closed off from us. It is, if we ever learn how to build the right ship, a place that one person could in principle traverse end to end, before they grow too old to walk. That is a strange and lovely thought. It is one of the things that, when I first encountered it as a teenager, I had to put down the book and look up at the ceiling for a long time before I could go on. It is a feeling worth letting yourself feel, in the dim quiet of the room, while you are warm under the blanket. The universe is enormous beyond ordinary human imagination. And it is also, in the most rigorous mathematical sense, the size of a single life. There is one piece of subtlety we should still address. Because of the expansion of the universe, the furthest galaxies are actually moving away from us. They are not just sitting still while we drive toward them. The space between them and us is stretching, and the further away they are, the faster they are receding. At some point, the receding speed becomes greater than the speed of light. Not because anything is moving through space faster than light, but because space itself is stretching at a rate that exceeds it. That sets a boundary on what is reachable, even in principle. Beyond a certain horizon, the universe is moving away from us so quickly that no signal we send will ever catch up. The galaxies beyond that horizon are, in the deepest sense, lost to us. They might as well not exist as far as any future descendant of ours is concerned. That horizon is, today, about 16 billion light-years away. It is closer than the edge of the observable universe, because what we can see and what we can reach are not the same thing. This particular detail was not really fully appreciated until the late 1990s, when astronomers studying distant supernovae discovered that the expansion of the universe is not slowing down, as everyone had assumed it would be. It is, instead, accelerating. The space between distant galaxies is stretching faster and faster as time goes on. The mysterious cause of that acceleration is what cosmologists now call dark energy, although the word energy is more or less a placeholder for something we still do not understand. The discovery, made by two independent teams of astronomers, led by the Australian physicist Brian Schmidt and the Americans Saul Perlmutter and Adam Rice, was so unexpected that they were given the Nobel Prize in 2011 for the work. The implication is uncomfortable. As the universe ages, the horizon of what is reachable will slowly shrink. Galaxies that are reachable today, in principle, will eventually slip beyond the boundary and become unreachable. no matter how fast a future spacecraft tries to chase them. Far into the future, an inhabitant of a galaxy like ours will look out into a sky that is almost completely empty. They will see only the nearby gravitationally bound galaxies. The rest of the universe will have, by then, slipped over the edge. That is a sobering thought. But it is also a reminder that the universe we live in right now is, in some sense, the most accessible version of the cosmos that will ever exist. The reach available to a human born today is the largest reach that will ever be available to anyone born after us. The window is, in cosmic terms, open. It will not stay open forever. So the actual largest distance a traveler could reach in a single lifetime is bounded by that horizon. Within those 16 billion light years, every point is, in principle, reachable, with enough acceleration. Beyond it, nothing is. That distinction is worth holding gently in your mind. The universe permits one human life to span an enormous reach. It does not permit one human life to span everything. Some of the universe is, even in principle, beyond us. Around the time this all becomes clear, most people start to feel a quiet mix of awe and humility. The awe comes from the sheer size of what is reachable. The humility comes from the sheer size of what is not. Both feelings, I think, are correct. Now, we should also spend a little while thinking about what it would be like to actually live through such a journey, if it were ever possible. Because that, too, is part of the question. Imagine the first day. The ship has just left the Earth. The acceleration is gentle but steady. From the inside, it feels like ordinary weight. You can walk around. You can pour a cup of tea. There is a small porthole on one side of the cabin. Through it, you can see the Earth, smaller and smaller, until it shrinks to the size of a marble. Then a grain of rice, then a fleck of dust, then nothing distinguishable from the other stars. The sun is the dominant light in the sky for a while. Then, after a few weeks of acceleration, it too begins to fade. It does not vanish. It just becomes one of the bright stars among many. There is a kind of unspoken finality to that moment. You are now, by any reasonable definition, no longer of the solar system. The constellations you grew up looking at are still recognizable from outside the solar system, more or less, because the stars in them are far away and your viewpoint has not yet shifted by much. But as the months pass, they begin, very slowly, to deform. Orion becomes a slightly different shape. Cassiopeia tilts. The familiar patterns become unfamiliar. The night sky becomes a foreign country. By the end of the first year, the ship is moving at 3/4 of the speed of light. By the end of the second, almost the full speed. From this point on, something visually striking begins to happen outside the windows. The light from the stars in front of you compresses, becoming bluer and brighter. The light from the stars behind you stretches, becoming redder and dimmer. The view ahead becomes a tight, intense circle of blue-white. The view behind becomes a slowly receding pool of red. The rest of the universe, on either side, is squeezed into a kind of ring of distorted color. This is what physicists call relativistic aberration. It is not an illusion. It is what your eyes would actually see if you looked out through the porthole. The cosmos, for the high-speed traveler, looks visibly different from the cosmos seen at rest. Inside the cabin, however, life is ordinary. You eat, you sleep, you read, you think. You begin to lose the easy sense of where you are. The destinations on the navigation screen are listed in light years. The clock on the wall shows ship time. The clock next to it, the Earth time clock, has begun to lurch ahead. Each day on board corresponds to longer and longer stretches of Earth days. After a few years of ship time, the Earth time clock is jumping forward by centuries each week. After 10 or 20 years of ship time, the Earth time clock is climbing by millions of years. The numbers become almost meaningless. The world you left behind is no longer there. You might keep a small notebook. You might write in it slowly, in the long, quiet evenings on board, about the people you remember. You might write down the names of your grandparents and your parents and the friends you used to walk to school with. You might write down what your kitchen smelled like in the autumn. You might write down the small tune your mother used to hum when she folded laundry. You might write all of this not to keep them alive, because you know perfectly well that they are gone, but to preserve a small private record of where you came from. The notebook would, in a way, be the truest map of where you have traveled. Not the maps on the navigation screen, which only show the great geometry of the stars, but the small notebook on the table next to your bed, which holds the shape of the world you left. The walls of the ship would, over the decades, become familiar in the way the walls of any long-lived home become familiar. You would know the scratch in the panel where you bumped into it once, years earlier. You would know the small place where the seal of the porthole has gathered a little dust. You would know the particular hum of the air recyclers in the late evening. The ship would become, in time, less a vehicle than a kind of slow apartment, drifting through emptiness with you inside it. Outside the windows, the universe would do what it does. Inside, you would simply live. The two things would, after a while, feel like different worlds, like two separate stories happening at the same time. This is the loneliest part of the picture, and it is worth acknowledging gently. The price of crossing the universe in a single life is the loss of any place to return to. Every voyage that approaches the speed of light is, by its nature, a one-way voyage. You cannot turn around and come back to a world that still recognizes you. You can come back to a world, but it will be a different world. The people you knew will be long dead. Their grandchildren's grandchildren will be long dead. The city you grew up in will be either rebuilt many times over, or covered in jungle, or under the sea, or buried under a glacier. The price of going far is the loss of home. That is not a small price. It is, in some ways, the largest price a person could pay. There is a parallel here to something simpler and quieter that all of us already know about. Every life is, in its own way, a long, slow voyage away from the home it began in. The child you once were is, in a real sense, no longer reachable. The bedroom you slept in at the age of 9, with whatever toys lined the shelf and whatever pattern the curtains had, is gone. The smell of your grandmother's kitchen, if you ever knew it, is gone. The friends you played with on a summer afternoon decades ago have grown into different people, scattered across different cities. You did not even need a starship to lose that home. The simple passage of time in the most ordinary life takes us away from where we began. The lights of the past dim, the faces of the past blur. The road behind closes up with grass. The traveler in the starship is, in some sense, only doing on a cosmic scale what every one of us does, slowly, on a much smaller scale, just by being alive. So perhaps the loss is less alien than it first seems. Perhaps the difference is just the rate at which it happens, and how much of the universe gets folded into the new shape of the life that follows. The starfarer loses a planet. The ordinary person loses a childhood. The size of the loss is different. The shape of the loss in the heart may be more similar than we think. There is, in both cases, something quietly precious about the going. There is, in both cases, something quietly precious about the having gone. And yet, When we step back from the price and look at the achievement, there is something quietly noble in it. The whole project of human spaceflight, slow and small as it is so far, points toward this possibility. Every spacecraft we have launched has been, in its own modest way, a step in this direction. From Sputnik in 1957, the first object to orbit the Earth, to the Vostok capsule that carried Yuri Gagarin into orbit in 1961, to the Apollo command module that brought the first humans to the Moon in 1969, to the long-duration stays on Mir and the International Space Station, to the robotic probes spreading out into the outer solar system. Each step has, in its own small way, expanded the radius of what a single human life can do. The number is still tiny compared to what the universe permits, but it is growing. There is a quiet line of poetry, written by the Russian rocket pioneer Tsiolkovsky we mentioned earlier, that says, "The Earth is the cradle of humanity, but one cannot live in a cradle forever." He wrote that in a small wooden house in Kaluga more than a century ago, before any rocket had ever flown above the trees. He wrote it without ever expecting to see what he was describing. But the sentence has stuck. It has been printed in textbooks. It has been carved into walls. It has been quoted by astronauts and engineers and dreamers in countries that did not exist when he wrote it. It captures simply the long arc of what we are slowly working on. Carl Sagan, decades later, would write another line that sits alongside Tsiolkovsky's in the long, quiet conversation. In 1990, the Voyager 1 spacecraft, then about 4 billion miles from Earth and on its way out of the solar system forever, was turned around for one last photograph. Sagan had spent years convincing the engineers to do it. The pictures the camera took were almost empty. Tiny specks of light scattered against the darkness. One of those specks, in one of the frames, was the Earth. From the distance Voyager had reached, the planet that had built the spacecraft was less than a single pixel wide. Sagan, looking at that picture later, called it the pale blue dot. He wrote about it in a book of the same name, which was published shortly before his death in 1996. He pointed out that everyone you have ever heard of, every leader, every saint, every villain, every grandmother, every child, has lived their entire life on that mote of dust. Every war ever fought, every love letter ever sent, every quiet supper between an old couple in a small kitchen, all of it, on that one dim point in the photograph. Voyager kept going. The Earth in the picture did not move. It just hung there, very small, very still, very fragile, as the camera lens looked back at home from a place that home could not, by any ordinary means, reach. We will probably never have another picture quite like that one. The Voyager probes are now too far away and too cold for their cameras to function. The next time someone in the solar system takes a photograph of the Earth from a comparable distance, it will be with a different spacecraft, in a different decade, possibly run by a different country. But the meaning of the picture is permanent. The pale blue dot, hanging in the middle of a beam of stray light, is a reminder of what the answer to tonight's question actually means. The cosmos is enormous. Our planet is small. The distance between them is, mathematically, crossable by a single human life. The distance between them is, in every practical sense, immense. Let me gently walk back through the answer to our question, so the shape of it becomes clear before we begin to close. The furthest a human being could, in principle, travel within a single lifetime, measured by their own clock, is about 16 billion light years. That is the edge of what is reachable, given the expansion of the universe. To reach that edge, they would need to accelerate continuously at roughly 1 Earth gravity for the entire journey, and then decelerate similarly for the second half. the total subjective time would be about 45 years. The total Earth time, by comparison, would be tens of billions of years. The Earth they left would, by then, be gone. The sun would have long since burned through the rest of its hydrogen. The continents would no longer exist. The galaxy itself would have merged with Andromeda, the two great spirals colliding into one enormous, slow whirlpool of stars. The price of reaching the edge of the visible universe is the loss of everything left behind. The reward is having seen the universe end to end, from the inside of a single life. If we were to scale the answer down to what is achievable today, the picture is very small. With our current rockets and current bodies, the furthest a human can go in a lifetime is approximately the distance to the moon, plus the cumulative distance of multiple long stays in low Earth orbit. That is, in cosmic terms, almost nothing. It is, in human terms, an extraordinary leap forward from where we were 100 years ago. Both statements are true at the same time. The universe is vast, and we are very young, and the gap between what is possible and what we have done is enormous. But the door is not closed. It is only slightly open, and we are still figuring out how to look through. There is one more reflection I want to share with you before the night winds down. The question of how far a human can travel in a lifetime is in some ways a question about the relationship between time and meaning. We are creatures whose lifetimes are short by cosmic measure, but we have built tools, languages, equations, and machines that reach far beyond our individual bodies. A single human life is short, but a single human life, through what it builds and what it leaves behind, can echo for thousands of years. Tsiolkovsky never flew. Goddard barely flew. Einstein never sat in a starship. And yet their work, taken together, lights the path for everything we have been describing tonight. They are part of the human reach, even though their bodies stayed close to the ground. The longest journey any of us takes is rarely with our feet. It is more often with our questions, our calculations, our patience, and our care. Let your shoulders settle now. The pillow is doing its job. The room is the size it has always been. The night outside is going on without you, slow and steady. You do not have to keep listening if you do not want to. The story will keep going gently, and if you drift off, it will simply be the soundtrack to the first dream of the night. There is an old story among amateur astronomers about the moment a person first really understands the scale of the universe. People describe it differently. Some say it feels like standing at the edge of a deep canyon for the first time. Some say it feels like looking out from a high cliff at the ocean. Some say it feels like the moment you realize, as a child, that the back of a closet does not actually lead anywhere. There is a quiet ache in all of these descriptions. The ache is the difference between how vast the world is and how small we are. But there is also, in all of them, a kind of comfort. Because the very fact that we can perceive that vastness, that we can put numbers on it, that we can write equations describing it, that we can carry it home with us and tell other people about it, is itself an answer to the smallness. We are small, and we know we are small, and in knowing, we are part of the universe that is large. There is one more figure worth mentioning before the night closes, because his life touched on so many of the questions we have been turning over. Stephen Hawking, born in Oxford on January 8th of 1942, exactly 300 years after Galileo's death, spent most of his career thinking about the most extreme objects in the universe. Black holes, the very beginning of time, the shape of space at the largest scales. He was diagnosed at the age of 21 with a motor neuron disease and was told he had only a few years to live. He lived for 55 more years. He could not walk. He eventually could not speak with his own voice. He communicated, in his later years, through a small computer mounted on his wheelchair, choosing words one at a time with a single muscle in his cheek. And yet, somehow, from the limits of that one slowly failing body, he reached further into the structure of space and time than almost anyone who had ever lived. He showed that black holes are not, in fact, perfectly black, but radiate a faint heat that we now call Hawking radiation. He wrote books that sold millions of copies to readers who could not always understand the equations, but who could feel the awe behind them. He took, in the years before his death in 2018, a brief flight on a small jet that simulated weightlessness, floating for a few short minutes as a man without a body in the country of the universe he had been thinking about for decades. His reach was, by every measure that matters, vast. He had not gone anywhere. He had been, for most of his life, sitting still. The lesson, like all the lessons in tonight's story, is gentle. The body is one kind of vehicle. The mind, paying careful attention, is another. Both can take us very far. If you bring all of this together, the question of how far a single human can travel begins to look different from how it looked when we started. The simple version is a number. 16 billion light years, give or take, given a perfect ship. That number is real, and it is staggering. But around that number lives a quieter picture. It is the picture of all the people, the small wooden houses, the careful equations, the small patient experiments, the quiet years of waiting, the spilled tea, the long pages of arithmetic, that have led collectively to our being able to write that number down at all. The actual reach of a single human life is not just the number of miles their body can cover. It is also the depth and the height of the questions they can ask, and the care with which they can think about the answers. Tsiolkovsky did not fly. Neither did Newton. Neither did Lorentz. Neither did Minkowski. Neither did Poincaré. Neither did Hawking. And yet they reached very far indeed. The full furthest distance, when you measure it properly, includes the journeys of the mind as well as the journeys of the body. And by that broader measure, our species has already, in its own small way, walked very far from the place where it began. The answer to tonight's question is, in the end, two answers. By the clocks of the people back home, even the most ambitious traveler could only reach the parts of the cosmos that are very nearby. By the clocks of the traveler herself, the whole reachable cosmos could fit within a single working life. Both answers are real. Both are the universe at its most honest. And we are the kind of creature that can hold both of them at the same time without breaking. Slowly now, let your awareness drift back to the room you are in. Notice the weight of your body against whatever surface is holding it. Notice the soft hum or silence of the air. Notice the warmth that has gathered under the blanket while we have been talking. The lamp on the bedside table, if there is one, is still steady. The clock on the wall, if there is one, is still slow. The world outside, beyond the windows, is still turning in its calm and ordinary way. You are exactly where you are supposed to be. Tomorrow, the question of distance will become small again. Tomorrow, the question will be about the trip to the kitchen or to the bus stop or to a friend's house across town. Those small distances are also part of the human story. Every long journey we have ever taken began with a short one. Tsiolkovsky walked from his little wooden house to the post office. Goddard walked from his bedroom to the cherry tree. Einstein walked from his desk in the patent office to the streetcar stop. Each of them lived ordinary lives in ordinary towns, and each of them, in the space of a single short human life, helped move the rest of us a tiny bit further out into the dark. The furthest a human can go is, in one sense, the edge of the universe. In another sense, it is just the next breath. The next slow, gentle breath you take, and the one after that, and the one after that, are all part of the same long journey. There is no urgency in any of it tonight. Sleep, when it comes, will come quietly. The stars will go on without us being awake to watch them. The galaxies will keep their slow turning. The universe will keep doing whatever it is the universe does. None of it requires you to stay awake. So let the question rest, just for tonight, like a small, smooth stone in a shallow bowl of water. Tomorrow, if you remember any of it, you can pick it up again. If you do not, the universe will not mind. It is, after all, the size it is, whether or not anyone is watching. And you are, after all, a small, warm creature in a quiet room, breathing slowly, drifting toward sleep with the distant, patient stars somewhere far above the roof. If your mind keeps wandering back to the numbers, that is fine. They are good numbers to wander with. 16 billion light years, 45 years of ship time, 1 Earth gravity of constant acceleration, a traveler aging at the same rate she always would, while the universe outside her windows stretches and compresses around her. Let those numbers turn slowly in the back of your mind, the way a child sometimes turns a kaleidoscope just before falling asleep. There is no hurry to put them down. There is no need to put them in any particular order. They are simply a quiet little collection of facts about the place we live in. They will keep without effort. The mind, when it is allowed to rest, tends to file the important things gently into the right, small drawers. Notice, if it is comfortable, the slow rise and fall of your chest. Notice the weight of your eyelids. Notice the way the room around you has dimmed during the time we have been talking. The walls are still there. The ceiling is still there. The floor, somewhere below the bed, is still there, doing exactly what floors do. Outside, somewhere far above the roof, the sky is still doing what the sky does. The stars are still slowly turning. The galaxies are still slowly drifting. The universe is still patiently being itself. None of it needs your attention tonight. None of it asks for anything from you. We have walked a long, slow road tonight. From a backyard under the stars, through the harbors of old explorers, through a small wooden house in Kaluga, through a patent office in Bern, through the launch pads of Cape Canaveral and Baikonur, through the strange compressed light of an imagined starship porthole, and back to the quiet room you are in right now. The walk was, in the end, less about the answer than about the company. The names of people who once cared about the question. The shape of the question itself, turned over in our hands like a smooth piece of polished stone. The feeling somewhere along the way of being part of a much larger story than any of us alone. You can let go of all of it now. The story will keep without you. The stars will keep without you. The blanket is warm. The room is safe. The night is long enough for everything. Good night, gently, from this side of the world to yours.